Hi, so welcome back. In this video, we will learn about second order linear ordinary differential equations, but of the non-homogeneous type. So in the previous few videos, we had learned second order linear ordinary differential equations, but which were homogeneous. In other words, if this is a second order linear ordinary differential equation, the right hand side, so for non-homogeneous, the right hand side would be a function of t, a function of the independent variable, where x here is a function of t or time. And if on the right hand side you have a non-zero function of time, then that would be called a non-homogeneous second order linear ordinary differential equation. Before this, for homogeneous, this part was zero. So if we sort of go back to the model on which this differential equation was studied, so this was the physical diagram, or one of the examples from which an differential equation of this kind arises. There are, as I said many times before, that there are various other examples which give rise to equations of this kind, differential equations of this kind. So a mass being suspended from a ceiling by a spring at any point of time t, the distance from the ceiling is x. There are forces, the spring force, which is the spring constant times the length of the spring. There is the eta with x prime, which sort of gives the resistance of the air as the body moves, or the friction. So that's the thing. And here, so before this capital F here is actually an external force which we are bringing into the system as we are studying non-homogeneous ODEs. Before this force was not there. In that case, the right-hand side would turn out to be zero. But because this is an external force which can be applied on a system, for example, gravity is an external force, somebody could be poking this body from above or down or whatever. It doesn't matter which direction the force is. You can always take a component either downwards or upwards. So let's, for this example, assume that the force is pointing downwards, perhaps with a minus sign. We don't know. So that's an external influence which sort of shows up on the right-hand side. Now, of course, I've changed this capital F to small f here, because if you go back to the video where we sort of started studying second order linear differential equations, when we sort of wrote down this differential equation from a diagram like this, we found that the right hand side was the external force divided by the mass of the body, capital F by m, which would be a different function because it's divided by another constant. So instead of that, but still a function of time, if capital F is a function of time. So instead of just that, so therefore we're writing the right hand side as small f, because small f would be capital F by m, which is the mass. The acceleration would be mass times, the force would be mass times the acceleration. So therefore, because this capital F is non-zero, external influence is definitely there. So the right hand side is non-zero, function of time. As an example, we can say that this is a second order linear ordinary differential equation of the non-homogeneous type, because the right hand side is an exponential function of time. So it's non-zero and it's a function of time. So alright, so now the question is, what do you do with a differential equation like it? Of course, as always, you solve it. In other words, find out what x is as a function of time. Well, before we study the theory of this a little bit, or go deeper into the theory of this non-homogeneous type second order linear differential equations, let's try and see if we can figure out a solution for this. Well, so I need some function of time which would fit this equation. In other words, instead of x, if I put that function, I would, if you worked all of this out, if you differentiated it twice, differentiated it once, multiply that by 5, if you did all of that, that function should spit out e to the power 4t. Now, what would be a function of time that would spit out exponential? Well, I can guess that it would be an exponential, because it doesn't matter if you differentiate an exponential once, twice, or whatever you do, you still get an exponential. So my first guess, or as I said before, a trial solution would be an exponential with the same index, because if you differentiate this, you get an exponential with the same index. If you differentiate it once, you differentiate it twice. Of course, you keep getting coefficients here. For example, if you differentiate it once, you will get 4, twice you will get 16, like that. But the core function remains the same. But of course, we don't know what this coefficient was going to be, because it has to undergo a lot of differentiations here. So we just want to, let's say I put alpha here, because I don't know if there is a weight that has to be added in front of it. So let's just say that this is the trial solution to solve. So we're solving this right now. We're solving this differential equation. So this, as I said, would be a trial solution. Still a trial solution because I don't know alpha. If I knew alpha exactly, so that this would then, this would fit this equation, then it would no longer be a trial solution, it would be the solution. So, alright, let's say I try this out. So instead of x, I put alpha e to the power 4t. I differentiate that twice, so I will get alpha. 4 comes down twice, so I will get a 16 e to the power 4t plus 5. Well, differentiate this once, so I will get 4 down here. I still have alpha, and I will have e to the power 4t plus 6 times this, no differentiation at all, so alpha e to the power 4t, and on the right hand side I have e to the power 4t. Well, something is common. E to the power 4t is common in all of these terms, so I can take that out. And since e to the power 4t exponentials are never 0, we have an exponential, exactly the same exponential, e to the power 4t on the right hand side, and it's non-zero, so we can cancel the whole thing out. So we don't have to bother about e to the power 4t in this differential equation, or in this algebraic equation now. Alpha is common from all of them, so I take out alpha. I'm not worried about, I forget all the e to the power 4t, so I get 16 from here, I get 5 times 4 is 20 from here, and I get 6 from here, and I get 1 because I have cancelled out e to the power 4t. So I know alpha exactly. You see, you add the whole thing, so this gives me alpha is 1 divided by, this is 36 plus 6 is 42. So alpha is 42. And so I can say that I know alpha, so I can just write down this value, which is 1 over 42, and it is no longer a trial solution. It is no longer a trial solution. In fact, it has a particular name. The name is that this would be a particular solution. So this kind of a function which you have found, mostly by inspection or your intuition, something that would fit and spit out e to the power 4t, this function, or as a solution, would be called a particular solution. In fact, I want to give it a suffix here, xp, just to specify that this is a particular solution of this differential equation. Of course, it will be a function of time, because t shows up on the right hand side. So if you can solve a differential equation of the non-homogeneous type, second order linear, by this kind of an inspection, what you would find is a particular solution. This method actually has a name. It's the method of undetermined coefficients. Let me just write that out. The method of undetermined coefficients. this method that we have used to solve or to find a particular solution, the undetermined coefficient here refers to the alpha. The alpha that we used here was undetermined as long as this was a trial solution, and then we put that in and we found exactly what alpha was. So we have determined the undetermined coefficient, and that was 1 over 42. Right. However, there are problems in this. What would happen if this was, instead of 4, if this was minus 3, for example? Right? In that case, we go back to what we did before. Let's just say, so again, we're doing it again, but with a minus 3 now. Let's say this is beta now, and this is minus 3. This is the undetermined coefficient beta, which we have to find. So this again becomes a trial solution for this differential equation. Now, if you do the same thing, well, let's just say beta, let's just say alpha, because I have alpha written out here. It doesn't matter. Now, if you do the same thing, we got 16 because we got 4 square. This time we will get a minus 3 square because the minus 3 is up here. So you will get a 9. We will get a minus 3. And we will get nothing from here. Sorry. And yeah, so all these 4s will become minus 3. Now, if I sort of do the same, eliminate e to the power minus 3 by the same argument, take out alpha, I have 9 minus 15, and then a plus 6, which is 1. But then this is plus 15 and minus 15. 9 plus 6 is plus 15. And so this is 0. But unlike before, I can't now divide by 0. But before it was 42, so I could divide easily and it was still valid. It was valid. But now I can't do that. So I can't find alpha by this method of undetermined coefficient if this 3 of this coefficient here, this factor here, is minus 3. So the process fails. So obviously there are problems. Okay? But as long as it was one of those factors which gave a non-zero, number here, then this, 1 by 42 e to the power 40 was a particular solution. So this method doesn't work for certain factors here. We will inspect all of them later. Okay? Now, right. So, what do we conclude? We conclude that if, say, we have a general type of equation where the input here, the right-hand side, the non-zero input, because it's non-homogeneous, is an exponential. So if x double prime, so now writing everything in general terms, if x double prime plus bx prime plus cx is equal to some exponential term on the right, let me make it very general now, some coefficient or amplitude of the exponential minus, or let's say plus small at. If this is a differential equation, second order linear differential equation, non-homogeneous, with an exponential input on the right hand side. This is with an exponential input. If you have a differential equation of this kind, then what would be the solution? The particular solution, xp, as long as this a square plus ba plus c is not 0. Okay, that's what we did. We got 3 square. So this is 3 square minus b is 5 minus 3 plus 6. Okay, that is c. So as long as small a square plus b a plus c is non-zero, the solution was capital A over a square plus b a plus capital C, e to the power small a(t). That's what we found, isn't it? Let's just go back to what we did. So this was the one where we could find 1 by 42. Here, there was 16 and there was a 4. There was 4. There was a 4. 4 and a 4. This was what we had initially. And of course, this was 4 square. Actually, let's write it as 4 square. 4 square plus 5 into 4 plus 6. So that is a small a square plus b into small a plus 6. As long as this is not 0, the factor here, alpha, is 1 by. So here, a was 1. Capital A here is 1. So we have 1 by 42. If you have a factor which is 5, for example, then you would have a 5 by 42, because then this 5 would show up here and would remain as 5 once you cancel out the e to the power 4t. So, right. So this is the particular solution when a square plus ba plus c is not equal to 0. So let's just box that. Okay. This is some formula that we have found. If you ever get a second order linear non-homogeneous ordinary differential equation with an exponential input of this very general kind, then the particular solution would be this, as long as this denominator is not 0. Okay, we will investigate the case when this is 0, and we will take that up in the next video. But before that, we will come back to a particular solution of this differential equation. We will say more about it. So let's just rub everything out and let's just go back to what we had started with. Right. Now suppose, so this is the differential equation, non-homogeneous. Non-homogeneous would mean that you have this external influence, non-zero influence. Now, if you make the right-hand side 0, or if you ignore this external influence on the system, then obviously this differential equation would become what we have studied in the last few videos. This is the homogeneous form. So if you ignore the force, external force, you get what is called, this is called the homogeneous form of the given differential equation. This is the homogeneous form of, if this differential equation is 1, homogeneous form of 1. Okay. Just ignore the right hand side, make it 0, and it would be called the homogeneous form of the given differential equation. Well, we have found general solutions for this. There was the case of underdamping, overdamping, undamped motions, critical damping or resonance, whatever they were. There were various cases, but we found what this was. Okay, the general solution for this we had found. Let me call that XH. In other words, XH is a solution for this. Instead of X, if you put xh, and if you did all of this, differentiated it twice, once here, multiplied by b, it would spit out 0. So say xh is a solution of this homogeneous form of the given differential equation. This has a name too, okay? This has a name. It's called the complementary function. Well, don't restrict yourselves in names right now, but I'll just have to, give it out. So it's called the complementary function of the given differential equation. For example, the one that we had studied. Well, the homogeneous form of this differential equation is making this 0. So what was the differential, what is the complementary function then? The complementary function would be just finding out the general solution for this, okay? Well, how did we find that out? This was the auxiliary equation, plus 5m plus 6 equals 0. So the two values of m1 would be, as it's very easy, this is m plus 2 and m plus 3. This does it, this factorization. So m1 is, say, minus 2 and m2 is minus 3. Okay. So for example, xh. So in this case, xh was, well, it can be one of them. Okay. I can have e to the power minus 2t, for example. This is a solution for this. If you put in 2, and you can refer to the previous videos where we had solved homogeneous differential equations, this would be a solution for this. So that's why I'm calling it xh, because it's solution of the homogeneous form. You can have another one. You can have e to the power minus 3t. This is another solution. Well, if you want, you can call it xh1, which is the one of the solutions of this, and xh2, which is another solution of the homogeneous form. Okay, so whatever it is, if you take one of these solutions, then what you can do is, if you sort of, well, I can combine the two, as I said before, and I can write that as xh, which then would be this would be the general solution of this, okay, which I can call xh. And this is actually the complementary function, the combination of the individual solutions for the homogeneous part. This is called the complementary function of this. So we've just worked out an example where we have found the complementary function of the initial given ordinary differential equation with this input. Okay, this is the complementary. If I call this 2, this would be called the complementary function of this differential equation with an exponential input. Right. So what's funny about these complementary functions is that if you have a particular function of this differential equation, you can freely add complementary functions to the particular function, and it would still remain a particular function. So let's see. So what did I just say? I'm going to rub this example out. It's just something that we have worked out just to tell you what exactly I mean by a complementary function, okay, of a given differential equation. This is what it is. Now, suppose you have a complementary function of this differential equation. In other words, a solution for the homogeneous form of this differential equation. Then, and let's say xp is a particular solution. In other words, xp is a solution of this differential equation, the way we have found out for an exponential input, for example. So if this is a particular solution, of 1, then I claim that xp plus, well, you can add some weight, something, beta times xh. This is also a particular solution of 1. In other words, you can, if you get a particular solution, you can freely add different weights of the complementary function. Well, this could be 1 also. Add or subtract, because beta could be negative. You can freely add different weights of the complementary function and it would still remain a particular function. So let's just do this. It's a very small calculation, but let's just establish this, and we will need this later. So just to, before this, what does it mean to say that this is a complementary function? It means that this xh satisfies this equation. So let's just write that down. This means that xh, if you put xh instead of x and double differentiated it, and multiply that by b and differentiated that once, and did all of this, you would get 0 because this would satisfy this. And particular solution would mean that this would satisfy this. So you would have xp double differentiation plus b xp once plus cxp would give me this function. So this is what it means to have these two in mathematical terms. So I just have to show that this is a particular solution. In other words, this would be satisfying this. That's what it means to be a particular solution. So let's just say, so instead of x, I put this whole thing in there, okay? So let's just do that. So what I do is, I take xp plus beta xh, I differentiate this twice, plus b, I differentiate this once, plus c, I keep this as it is, and I want to show that this will be ft. Then I would have established that this is a particular solution of this. So let's do that. Double differentiation of addition of two functions is the addition of the differentiations of individual differentiations. So I would have xp double prime plus beta is a constant xh double prime plus b, this is b, don't confuse between beta and b. Sorry about the notations here, but I'll have a long tail for beta just for the distinction. B, this is differentiation of addition of two functions, so I will differentiate them and add them. This is what it means. Plus c, well, no differentiation here, so I'll just keep things as they are. Well, what do I get here? Can I group the particular solution parts here? So I will get xp double prime plus b xp prime from here, and a c xp from there. And what about these, the the complementary functions parts? So I will have, well, for all of these, you will have beta common, beta xh double prime, beta xh prime, beta xh. So let's just take that out. So what you will be left with, once you group these three terms, you will be left with xh double prime plus this multiplies with b, capital B, and you have xh prime. And then beta is out, so this multiplies with c, so you have a c xh. Well, what is this going to be? Well, we know this. This is this. It is ft plus beta times, what is this? This is this, 0. Well, this is, the whole thing is 0. So this is going to be ft. And so this, once you put in here, actually gives you ft. And so this is a particular solution. So it's a very important result. So now I can write it as a result. It's no more a claim. It's an important result that if you can establish somehow by inspection, or other methods, if you can establish a particular solution, you always know what is a complementary function because we have already solved how to solve, or we have learned how to solve homogeneous differential equations. So just make the non-homogeneous equation homogeneous and find out the complementary function. So once you establish this and you already know this, you can freely add any weight of the complementary function and you would still have this as a particular solution. So I think we will finish with this one here. This is one of the results we will need to investigate the case when alpha in the previous board was 0. So when we took e to the power minus 3, then the coefficient of alpha became 0. So there was a problem there. So we have to solve that problem. So this is one of the results that will come in handy when we do that. Okay. So I think we will finish it here. We will take things forward in the next video. Thank you.